Alright, we've got a first fatigue problem under bolts. There's a few specific things that apply to fatigue problems in bolted connections, and one of them, sort of interestingly, is that it's generally assumed that alternating loads in shear get absorbed by the friction. That is, even if you're relying on the joint to carry the shear by the bolts, if you've designed it that way, there should still be enough friction produced by the preload on the bolts to minimize the actual movement. And if you don't get movement, you're not going to get load into the bolts, which alternates. So all that is to say, if you have shear and tension in a joint, it's usually the tension that actually drives fatigue calculations. And that's what we're going to look at here. This is just a single 1-inch diameter UNC bolt, grade 5. It has cut threads, which the very first thing I'm going to do is note that I'm solving this problem with rolled threads. I don't have a good way of notating it on here, but right there it says cut. I'm going to treat this as rolled. The next problem I'm going to do will have cut threads, but this is a rolled thread problem. I'll note it on the next page too. Negligible bending, all that means is all we have is axial loads in this bolt. And we want to estimate the maximum external load that would prevent bolt separation and the maximum P for infinite life, which is what we're really interested in here. Before I jump into this, I'll jump over to the notes real quick and just remind you that these two tables give you some interesting properties for fatigue calculations. Table 816 gives some stress concentrations, and these are used for various things. The fillet is actually the area underneath the head of the bolt, which would be a separate sort of situation than what we're dealing with here. We're doing calculations at the threads. For cut threads, if they're machined that way, you have certain values. Rolled threads have lower values because it's a cleaner machining process. And then table 817 actually gives modified endurance limits or endurance strengths for some values here. And for all of these, you note down here at the bottom it says the KF, the stress fatigue factor essentially, has already been included. So we don't have to include the stress concentration from 816 here. But 816, as you can see, is only for rolled threads right there. So if you have rolled threads on a bolt and it falls into one of these classes, you can get the endurance strength from this table. If it has cut threads or if it's from some oddball class, you'll have to calculate the endurance limit through traditional practices. Alright, so we've got that 1/8 grade 16 bolt. I'm going to just go ahead and say again, this is for rolled threads, not cut. And we'll proceed from there. Now, the first thing I'm going to deal with is this torque. If you refer back to the torque control equations in the notes, torque is equal to K, which is a friction constant, times the initial force times the bolt diameter. And it's that initial force that we're actually looking for. K for a dry material or dry installation is .2. The torque, I just want to make sure I've got this in inch pounds to match units, so I'll multiply by 12. Got Fi, and we got our 1-inch diameter. From that, we'll get the Fi value as 6,000 pounds. And I didn't mention at the start, but we've got AT, SE, and SUT already pulled for this problem as well. Now, to calculate C, we were given in the initial problem, we're given Kc as a factor of Kb. Kc is 3 times Kb. And I should note too, Kc is a notation in a couple of other textbooks, so sometimes I flip those, but Km is what Shigley uses, same thing here. So it's going to be Kb divided by Kb plus Km, which is 3 Kb, or 0.25, 1/4. Now to calculate the alternating and mean stresses, we've got equations that go straight to this because our force in the problem statement is going from zero load to some maximum load. That's what I'm going to assume. I don't have anything to imply otherwise there, so force goes from 0 to some maximum value of P, which we'll just call P here. So in the notes there's equations for alternating and mean stresses where you have a variance between a maximum and a minimum. Here, since we just have a maximum, those are simplified a little bit. And we have an alternating stress given as C times that max value P divided by 2AT. And then the mean stress is given as the sigma A plus Fi over AT. So essentially here it's still alternating. You know, you've got the alternating value, but you've bumped the whole curve up by the initial stress in the bolt. So we have all the values here except for P. We're setting this up as a variable of P, as that's what we're solving. And that value, 6,000 over .606, is a constant of 9,901. So we're actually set up now to put all of this into directly the Goodman equation. We've got the endurance limit, ultimate strength, a value for sigma A, a value for sigma M, and we're going to just kind of put it up here as another assumption that factor of safety for infinite life, we're just going to set it equal to 1 right now. So into the Goodman equation with this. And since we just said the factor is 1, that'll just be equal to 1. So F dot 2063P over 18,600 plus dot 2063P plus 9901 over 120,000 is equal to 1. We solve for P, it's 71,620 pounds. So that would be the external load you can apply to this thing before, or rather, that's the maximum external load to have an infinite life. Now real quick, I'm going to do one more thing from the notes themselves, or rather the textbook really. There's a equation for factor of safety particular to the situation where you're varying from a zero force to a maximum value of P. If you're in that situation, you don't have to calculate the stresses explicitly if you use this form here. I don't remember the equation number on this, but it's right in the same section. Alright, so we have all those values. We have Fi, At, strength values, C, and then we got P right there to solve for. So if we would set this equal to 1 and solve it, we actually get the exact same value. So as long as your force varies from 0 to a max, that is, it's a repeated load, that equation works fine. Now the next part of this was at what force does joint separation occur? For that we need the formula for the joint force, which looks like that. This gives a compressive force, so it is negative. But we just want to set it equal to 0. That'll give us the value of P at which the joint is, basically there's no compressive force left. And Fi was 6,000. And solving that, we get P equal to 8,000. That's actually kind of interesting. When you compare those two numbers, we got was a factor of 9 or so increase. In other words, the joint will separate well before fatigue loading is actually an issue. That kind of gives a certain indication that if loss of compression is an issue, this bolt is larger than it needs to be. It certainly includes, if nothing else, a hefty factor of safety in terms of fatigue. So you could never load anywhere near the infinite life load, and certainly not exceed it before the joint separated. So it's not a very stiff joint, but it is a very strong joint.